So let's talk about surface area in section 15.4. What I want to do is find the area of surfaces above a certain domain. And I thought I would, instead of starting out with theory, I thought I would start out with an example first. So in the book, they give you the area of a surface defined over a region D to be the square root of f sub x squared plus f sub y squared plus 1 dA over D. All right. So z equals f of x, y is going to be my surface. And then my region D, so you have some surface like this one over a region D. So I said I wasn't going to go into theory first, but here I am. Just a little sketch first. So you have the surface here, you're going to find the area, and your region D might be something in the xy plane like this. And so you're just going to find the area of the surface above that. All right, so this is your region D. This dA here, of course, is the area, little area element of D. So you'll split D up into little hash marks, and then dA will be a little certain one there. All right, so what you'll do is you'll take the derivative with respect to x, square it, derivative with respect to y, and square it. Add 1, take the square root of that. Double integral over the region D. So this region D will be something in the xy plane. All right, so let's do an example of this, and then I'll show you where all this comes from. So what I want to do is this one. It's number 9 in the book. There's a video associated to it. I didn't watch it, just wanted to do it. I thought it was kind of a cool problem because I like this surface. Now, you know the surface. You don't have to know what the surface looks like, but if you look at it, when x equals y, then you're going to have z equals x squared or z equals y squared if you want. So there, you know there's going to be some sort of parabolic shape to this. And then when x or y is 0, you're going to get z equals 0. So it's going to be a parabolic shape, but then on the xy axes, it's going to hit those axes. All right. Okay, so it's this surface here that lies within the cylinder, x squared plus y squared equals 1. So there's a cylinder underneath this. There's a cylinder under here that comes up like this. And you're finding the area of the surface in there. So it's going to look like kind of like a potato chip. It's kind of hard to draw, but you're finding the area of that. All right, so let's try this out. So this z equals f of xy. So f sub x, this is equal to xy. So f sub x is y, and f sub y is x. So the area of the surface is the double integral over that cylinder, x squared plus y squared equals 1. Square root of f sub x is y, so you get y squared. I'm just using this formula here. F sub y is x, so that's plus x squared, and then plus 1 dA. All right, so since we're integrating over a circle, it's a cylinder, it's the area of the circle inside the cylinder, but this is a circle. We're going to use polar coordinates. It's just much easier to work with. So I'm going to change all this. It's going to be, it doesn't say first quadrant or anything, so it's going to be all the way around. So here we go, square root, y squared plus x squared is r squared, and then we have plus 1, and then r d theta for the dA piece. X squared plus y squared is 1 is a circle, so this is going to go 0 to 2 pi, and then 0 to 1. Now, I can maybe multiply this by 4 and make it 0 to pi over 2, but I'm not sure of the symmetry here, so I'm going to leave it as it is. It's not going to make it much easier if I did that anyway. So at this point, since there's no theta in the limits of integration, and there's no theta in the integrand, then I can pull my theta out and separate it. This is 0 to 2 pi d theta times integral 0 to 1. And now I'm going to go ahead and put this r in front, r square root of r squared plus 1 dr. And then this here, it just becomes theta from 0 to 2 pi. So this just becomes 2 pi times. Now it looks like a nice little u substitution here. U equals r squared plus 1. Du is 2r dr. 1/2 du is r dr. So this here all becomes 1/2 integral square root of u, which is u to the 1/2 power. All right. When r is, I'm going to change the limits of integration. So when r is 1, u is 2. When r is 0, u is 1. So my u integral goes from 1 to 2. This is du. All right. And so now this is u to the 3/2 divided by 2/3 times 1/2. Evaluate from 1 to 2. I haven't forgot about this 2 pi. So this is 1/2 times 3/2. Wait, I'm sorry. This is 3/2. I was going too fast. 3/2. This is now 2/3. 2/3, and then u to the 3/2 from 1 to 2. These twos cancel, and I get 1/3. 2 to the 3/2 minus 1 to the 3/2, which is 1. 2 to the 3/2 is 2 root 2. 2 root 2 minus 1. Here we go. 2 to the 3/2. Remember, it's like this. It's inside over outside. Outside is 2. Inside is 2 cubed. So that's square root of 2 cubed is 4 times 2. Square root of 4 is 2. So it's 2 square root of 2. So we get that. We multiply by that 2 pi. And so we get 2 pi times this 1/3. So it's 2 pi over 3 times 2 root 2 minus 1. And that's the answer. So there we have it. Now, what I want to impress upon you is that you don't need to know what this looks like, all right? You don't need to know. You're just working with the formula here, okay? So just work with the formula and you got it. All right, so I want to take this one. I want to do this one. The part of the sphere that lies above the plane z equals 1. So you got a sphere, and then it lies above the plane z equals 1. So I'm going to draw this sphere above the plane z equals 1. So what I'll do is, let me draw the sphere. It's just the top half of it. I'm just going to draw the top half, not really to scale here. But the top half, because it doesn't matter, because it's just the part of the sphere above the plane z equals 1. The plane z equals 1 is the plane that's parallel to the xy plane up 1 in the z direction. So it's just going to be the intersection of those two, like this. So it's going to be this little top piece of the sphere right here. All right. So we're going to find the surface area of that. So it's just a little piece like this. All right. So we're finding the surface area of it. So we need to find out what the domain is underneath it, right? Because there's a domain underneath this. So when you project this down into the xy plane, okay, so that's the top half of that sphere, top portion of the sphere above z equals 1. When you project it down into the xy plane, there is going to be a little domain there as well. So let's see. Yeah. So It's going to be like this. It's going to go all the way around. It's going to be right below it. So I'm drawing it too big. Anyway, the way you can look at this is the following. In the XY plane, you have the original sphere here that's projected straight down. That sphere, that's going to be where z is 0. That sphere has a radius of 2. So when you project the sphere down into the XY plane, this has a radius of 2. Now, when z equals 1, now I'm going to change z to 1. X squared plus y squared plus 1 squared equals 4. We get x squared plus y squared equals 3. So the radius is going to be the square root of 3, which is 1.7. Not 3, this is a 2. So the radius of the top piece, this radius here, this circle there is going to be 1.7. So it's going to be this here. So this is my domain D. This is D, which is what we integrate over that. All right. There we go. You integrate over that. So what's happening in 3 space is the following. You have that outside circle like that, and then you have this inside circle here like that. And this is what we're integrating over like that. Okay, so we're integrating over this, and what we're integrating is this sphere. So what is going, so now we take that and we apply our function to it. So it's x squared plus y squared plus z squared equals 4. Now the area function involves f sub x and f sub y, right? It's this double integral. F sub x squared plus f sub y squared plus 1 dA. So I need to solve for this z. So z is going to be the square root of 4 minus x squared minus y squared. Or z is 4 minus x squared minus y squared to the 1/2 power. So now, whenever I take z sub x, which is just f sub x, okay? It's just f sub x. So z sub x will be 1/2 times 4 minus x squared. Let me make this smaller. Y is gone. No, sorry, we're not taking the derivative yet. 4 minus x squared minus y squared to the negative 1/2 power times negative 2x, which ends up being, let's see, the 2's cancel right there. And now we get negative x over the square root of 4 minus x squared minus y squared. Now, x and y are interchangeable up here. So the z sub y will be the same thing, but switch things out. So then z sub y will be negative y over the square root of 4 minus x squared minus y squared. Now, in the formula, you square these two. Okay? You square them, and then you add them, and then you add 1. So let's do that. So we're going to take those, we're going to square them and add them. So z sub x squared plus z sub y squared plus 1, that will be equal. I'm just taking care of what's inside the square root. That will be x squared plus y squared over this. Now, when I square the bottom, I get 4 minus x squared minus y squared, and then I add this 1 here. All right. So at this point, we can bring r into it. Well, I tell you what, let me combine these up. Now this becomes x squared plus y squared plus 4 minus x squared minus y squared all over 4 minus x squared minus y squared. the way I went from here to here is I used my fact that if I have A over B plus C over D, I just cross multiply AD plus BC, and then I multiply the denominators together. This 1 is 1 over 1. So I'm here, I can cross out the x and the y's, those are gone. And so all of that just becomes 4 over 4 minus x squared minus y squared. All right. Okay. So now that is what is inside our area formula. Our area formula is this double integral there. So that's what's inside of it. So then my area of my surface is then, let's do this in a different color. So the area, so therefore area of the surface is double integral over that inner circle, x squared plus y squared equals 3, square root of all this, 4 over 4 minus x squared minus y squared, and then dA. Now this looks really gross, but it's not so much if you use polar coordinates. So polar coordinates will save the day for us. This will be 0 to pi over 2 pi. I think we want the full meal deal here, don't we? Yeah, all the way around. Part of the sphere that lies above the plane. Yeah, all of it. So 0 to 2 pi, and then r goes from 0 to root 3. And now this is the square root of 4 on top, that's just 2. And then this is the square root of 4 minus r squared. That's because x squared plus y squared is r squared. Okay? So I'm replacing all of this with negative r squared. And now this dA piece here just becomes r dr d theta. Now we run into the same thing we did before. There's not a theta in the limits of integration, and there's not a theta in the integrand either. So I can take this d theta and I can move it right there. And we saw before that the integral from 0 to 2 pi of d theta was just 2 pi. So convince yourself of that. So we got 0 root 3 of, I'm going to pull this, no, I'll leave the 2 there. I'll leave the 2 there. This is 2r. Let's go ahead and make that 2r times 4 minus r squared to the negative 1/2 power, and then dr. So at this point, it looks like we got u substitution coming. Let u be 4 minus r squared. Du is negative 2r dr, and then negative 1/2 du. Oh, well, no, wait, negative du. Yeah, how about that? Just negative du is 2r dr, and that'll take care of the 2r and the dr together. So what we get then is 2 pi integral. The 2r dr is being taken up by this du, so it's negative, and then du, and then it looks like u to the negative 1/2 power. U to the negative 1/2 power. Yeah, because u is 4 minus r squared. And now let's change the limits. When r is root 3, u is 1. So then u equals 1. When r is 0, u equals 4. This is perfect because now this goes from 4 to 1. Bottom limit of integration is bigger than the top one, so you flip them, that takes care of this negative. So this 2 pi integral 1 to 4 u to the negative 1/2 du. So this is 2 pi. All right, here we go. Add 1, divide by it. So it's u to the 1/2 divided by 1/2 from 1 to 4. And now this is 2 pi times 1/2 would be 4 pi. And then apply the 4 and the 1 to the 1/2, so that's 4 to the 1/2 minus 1 to the 1/2 power. That's 2 minus 1. This is 2 minus 1, which is 1, so we get 4 pi out of this. And that's the answer. So apparently, if you take a sphere and it's centered at the origin, and the sphere has a radius of 4, and you cut it with a plane that's at 1, so you end up just getting the top part of the sphere. Let me draw it in a different color. How about green? All right, go around. So you look at the top part of the sphere, and you find that area. I guess it's like the top of someone's head. That area, and this is z equals 1 here. This here is 4. I'm sorry, radius of 2. Then the surface area of the green part is 4 pi. All right, so what I want to go over now is the theory behind this. It won't take long. I really want you to watch this and understand it, because if you can understand this, this will really help the stuff from before and the stuff that's coming up. So what we have is we have a surface here. I'm going to call it z equals f of xy. It's this one right here. And I want to find the surface area of this. So what I'm going to do to find the surface area is I'm going to take it and I'm going to pick a point in every little hash mark that I have. Let me switch this out here. Hang on 1 second. I took care. Let me get this back purple. I'm going to take a point in every crosshatch of this, subinterval, and I'm going to find the tangent plane there, and that's what's here in black. So then I'm going to find the area of that tangent plane. So I've got my tangent plane there. I'm going to find the area of the tangent plane. Now, as a little trailer to this, the tangent plane is just a it can be formed using 2 vectors. A plane can be formed using 2 vectors. And when you cross those 2 vectors, like see, I'm using the parallelogram law of vectors. When you do the cross product of those 2 vectors, you get another vector. Let's call that n. And the length of n will be the area inside here. All right, so that's what we're looking at. We just have to identify what these 2 vectors are. So what I'm going to do is I'm going to take this P and this tangent plane, and I want to move them over. And just imagine that the tangent plane is here. All right. Now, this tangent plane is going to be formed by these vectors. So I don't really want to draw it too heavily, but I do kind of want to give you the idea here. These 2 vectors here in red and green, they're here. And the tangent plane is formed by those 2 vectors. It's a linear, let me say this, these 2 vectors are in the tangent plane. Let's put it that way. So the tangent plane that you don't see here, the surface is in here, you just don't see it. This point P is on the surface though, okay? The tangent plane is kind of like, maybe it's, how do I draw this without messing it up? Let me just redraw them. Over here on the side, it's more like this. Did I do it over there? No. It's like this. The tangent plane is in here, like this. All right, and I'm trying to find the area of this tangent plane. So I need this vector n. which is coming out of it. Like this. This is what I'm looking for. All right, that's there. So that's the plane that you're not seeing. It's not horizontal, okay? All right, so this is key. The key to understanding this is this figure here. The x bar is the red one. Y bar is the green one. X bar, this vector is going up. And if you study this for a second, you can see that there is an angle theta that is above the horizontal plane there. Let me just call that theta for a second. All right, so that theta angle is the angle that that vector is pointing up over the horizontal. This other angle over here, let's call this one phi. That one there is the angle that y is above the horizontal. I have drawn, so if you look at this delta z here, that delta z is the change in the z direction that the vector is going up in the vertical. And that, see the delta x here, this delta x is the change in the horizontal that you go along to form this vector. So I've drawn this, I think I drew this somewhere else. Yeah, I drew this here. So the same scenario is right there. So the angle, the slope that the vector x, this is the vector x, is going up in the z direction is the rise over the run. So it's the change in z over the change in x, rise over the run. Okay, but that's also the partial derivative of f with respect to x at the point P. So let me go back to the figure. You have your figure, and it's z equals f of xy. If you take at the point P here, at the point P, if you go in the strict x direction from there, like the red, if you go in the strict x direction, the slope there is f sub x. So this f sub x at a point P, this is the slope of the, let's say, the vector in the x direction. It's basically the slope of your surface. Then the vector is on the surface. It's on a tangent. How can I put this? It's the slope of the surface in that x direction. All right, and that vector kind of represents it in a very small area. So f sub x is that slope. There was an animation of this. I'll show you. Yeah, so let me pull over the little animation that you might have seen before. You see this surface that looks like a part of a paraboloid. See how this this plane that's here is not the tangent plane, it's the plane that's cutting it vertically. See how this line here, you can represent this as a vector. The line pretty much shows you how that surface is sloping. That line there, notice that it is in the strict x direction. The slope of that line is f sub x at the point P. At the point P, the slope will change as you go along this, plane. But at the point P, the slope of that line is f sub x, and then the directional derivative said, okay, well, I can move this around, and then the slope will change depending on where you're at. So here, while I'm at it, the slope of the line in the strict y direction, that'll be f sub y. So my red vector in my drawing is is this one basically, and my green vector is this one. And those two vectors form a plane. That's that black plane that I've been talking about. So the slope is f sub x of this vector, x, but it's also delta z over delta x. So delta z over delta x is equal to f sub x. So if I cross multiply, this is over 1, right? If I cross multiply, I get delta z equals f sub x at my point P times delta x. So essentially, this delta x here is your derivative at the point P times delta x. You've seen this before. It's in Cal 1. In Cal 1, you had some sort of nice curve, and then you had a tangent line to the curve. That tangent line was a hypotenuse of a triangle. All right, the horizontal piece of that of the triangle, the horizontal leg was delta x, and this is delta y. The slope of that hypotenuse was f prime of x. So you had delta y over delta x, the slope, that was f prime of x. So if you cross multiply, delta y was f prime of x times delta x. So the slope of the hypotenuse times the change in the horizontal direction was the change in the vertical direction. You saw this in like differentials. Okay, so that's what's happening in this scenario, but in this scenario, the delta y is delta z. So we have a very similar situation. The derivative piece times delta x is the vertical change. All right, so then this x bar vector can be written as delta x 0 delta z, right? Because the vector itself, let me show you that. The vector itself, if I draw the scenario again here, here's x, and this is z, then it can be expressed using the x component, delta x, and the y component, in this case the z component, delta z. So that vector would be delta x comma delta z. All right, but it's in 3 space, so there's a y here, which is 0. It's in the strict x direction, not the y direction. So here's my vector that represents x bar. That's x bar. All right. But delta z, we saw that was this. So I'm going to take that and I'm going to replace the delta z with that. All right. So then, similarly, all right, so what I'm going to do is I'm going to take out that delta x and I'm going to put it there. I took it out of here and here. All right, so x bar is 1, 0, f sub x as a vector, and then times delta x. Now, I can do the same business with y, and I get 0, 1, so this 1 and the 0 switch, 0, 1, f sub y of p delta y. I would invite you to stop the video and draw the scenario with your this is x here, this is y, this is z, with the green vector. All right, the green vector, this is delta y, this is delta z, and so the vector there is 0 in the x direction, delta y, and then delta z, like that. That's how that one's formed, right? Because this is delta z. And then the same business works. This is f sub y at p, and then you work it out. All right, so now I take out the delta y. All right, so if you do the cross product of these two, which we're interested in the cross product of those because the cross product of x and y will give me my n vector. And if this is x bar and this is y bar, then when you cross them, I don't know if I drew this exactly according to the right-hand rule, but that's the idea. In fact, I know I didn't. It should be one the other way, but just imagine for a second this is right. It should be going down, but the idea is that the area of that tangent plane is going to be the length of n. So we need to cross product these. We need to cross them. So when you do that, you get this here. So pause the video for a second and see that that's the cross product. All right, so there's the cross product. And now the length of n will be each one of these squared. This one squared plus this one squared plus this one squared, which is what I get on the interior. When you take the cross product and you find the length of it, right? Whatever constants you have on the outside, those just come for free. You don't need to do anything with those. You just set them on the outside. This comes from the fact that if you have a number times a vector and you want to find the length of it, this is just the absolute value of the number times the length of the vector. I don't need to do absolute value of these because the area pieces are positive. All right, so there you go. So that is this delta x, delta y. This is delta a, right? These are the lengths here of the two vectors. See, what you have is you have your vector x bar, and then you have your vector y bar. And then delta x goes in this direction, and delta y goes in this direction. This is delta y. And so your tangent plane, your little piece of area there is all of this. This is delta A. So length times width, right? So that's that. All right. So what I did was I simplified it. F sub x of p. I just wrote it as f sub x. All right. So, and then it's all explained here. So we take all those little tangent planes and we add them up, all those little pieces. Now, keep in mind, these tangent planes are finite, right? They're not the whole tangent plane. It's just a little piece that approximates above an area of the surface. And so that's how you get this. All right, and so that's the theory behind it. We are going to be using this extensively in chapter 16, so please get to know it.